Hey, welcome to The Explainer. Today, we're going to break down the physics of impact. What really happens when things crash, bounce, and smash into each other. Think about it. From a simple fender bender to the mind-boggling collisions of subatomic particles. These impacts are a fundamental part of how our universe works. They're happening constantly, everywhere. And even though they can look totally chaotic, there's actually a beautiful underlying order to it all. To really get what's going on, we have to start with one single, absolutely unbreakable law. Okay, let's get right to it. Our journey starts with this huge concept, momentum. You can kind of think of it as the amount of oomph an object has. It's just its mass times its velocity. And the most basic rule is that this oomph, this momentum, is always conserved. So, first things first. To analyze a collision cleanly, physicists love to imagine it happening inside this perfect little bubble, with no outside forces like friction or gravity messing things up. We call that an isolated system. It just lets us see the pure interaction. And here it is. This is the golden rule. No matter what, the total momentum of everything inside that bubble before the collision has to equal the total momentum after. Every single time. That part is totally non-negotiable. But while momentum is our constant, there's another player in the game, kinetic energy, the energy of motion. And this is what creates a fork in the road, splitting the entire world of collisions into two very different types. So, here's that fork in the road laid out for us. Look, on both sides for elastic and inelastic collisions, momentum is conserved. That rule always holds true. But check out kinetic energy. For an elastic collision, it's conserved. For an inelastic one, it's not. And that one little difference, well, it changes everything. All right, let's head down that first path. The perfect energy-saving collision. The kind of collision physicists dream about. So in one of these elastic collisions, objects bounce off each other perfectly. There's no crushing, no deforming, and no loss of motion energy. The classic example is two billiard balls. They just click together, transfer their momentum, and bounce away, and the total kinetic energy of the whole system stays exactly the same. Okay, so that's the perfect world. Now let's get back to our world, the other path, which is where pretty much every collision you've ever seen actually happens. Right? This is reality. In an inelastic collision, momentum is still conserved. Remember, that's our constant, but some of that kinetic energy, it gets lost. So the big question is, where does it go? Well, it doesn't just vanish into thin air. It transforms. That loud crunch you hear in a car crash, that's energy. The heat you'd feel from the twisted metal, that's energy. All that work it took to bend and deform the cars, that's all your lost kinetic energy, just changed into different forms. And once you start looking for them, you see these collisions everywhere. Two cars that stick together after a crash, a golf ball that actually squishes against the club for a split second, or even just a basketball that doesn't bounce back up to the same height you dropped it from. They all lose kinetic energy. So how can we be totally sure what we're looking at? How do we actually prove whether a collision is one type or the other, especially if we can't always trust our eyes? Let's get our hands dirty with an actual example. We've got two carts here. We know their masses, m and 2m, and we know exactly how fast they're going before they hit. They are on a collision course. First up, we pull out our golden rule, conservation of momentum. What you're seeing here is us setting the total momentum before the crash equal to the total momentum after. A little bit of algebra, and we can solve for that unknown final speed of the second cart. Now, hold on. You might be looking at this and thinking, okay, easy. They bounced off each other, so it's got to be elastic, right? Well, not so fast. That's a classic trap. Appearances can be deceiving, and in physics, we need cold, hard proof. And the real proof, the moment of truth, is all in the energy. We use that kinetic energy formula, 1/2 mv squared, to figure out the total energy of the whole system before they hit. And then we do it again for after they hit. The big question is, are those two numbers the same? And there you have it. The math doesn't lie. The after energy is less than the before energy. It's right there in black and white. Kinetic energy was lost. And that means, even though they bounced, this was for sure an inelastic collision. Okay, so we've totally cracked the code for a simple straight line collision. But, the real world is rarely that simple. So what happens when we expand our view beyond just one dimension? It's actually pretty cool how this works. When things collide on a flat surface, like at a four-way stop, our momentum rule still holds up. We just have to apply it twice. Once for all the east-west motion, the x direction, and again for all the north-south motion, the y direction. Momentum is conserved in each direction, separately. And once you get that, you can unlock some seriously complex stuff. Over on the left, we could figure out the final speed and direction of those cars after they T-bone. And on the right, that's a classic physics problem called a ballistic pendulum. It's a collision followed by a swing, and we use both conservation of momentum for the impact and conservation of energy for the swing. The same core ideas solve it all. So here's the big takeaway. The next time you see a car brake hard, or a ball bounce, or even just watch a game of pool, you'll know the secret. Momentum is always conserved. But look a little closer. Did you hear a sound? Did anything get bent or squished? Because the energy tells you the rest of the story.